Okay, the last device that we're going to talk about in these lectures is this simple device called an SR latch. And really what this is a 1-bit memory device. And the operation is really simple. S stands for set, R stands for reset, and the output Q. Sometimes there's a Q naught also, but that's the output. So this is how it works. If we pulse a high input to the set, the Q goes to 1. If we then set a pulse to the reset, Q goes to 0 and stays there even if the signal goes low. So basically what we can do is use that to control the Q output at different periods of time to remember a bit of data. Now, if we took 8 of these SR latches and connected them together in parallel, we'd have a 1-byte memory device. And it's assumed that all the sets and resets are connected together. So you'd have a set and a reset, and then 8 bits of data here. So that's 1 byte. If we wanted 64 bytes, we'd have to basically add 64 of these together. So pretty quickly you can see when you start talking about gigabytes of RAM or data, each bit requires this device. So it starts to get very large very quickly. So what does the inside of an SR latch look like? Well, essentially what it is 2 cross-coupled NOR gates. You can't really have a method of storing data or having what is called sequential logic, which is clocked logic, without taking the output of one device and going to the input of the other. So let me clean this up a little bit. A little OCD with this drawing, even though it's far from perfect. But let's say we start with a condition here where the input is 0 on the top NOR gate. I'm going to have the truth table there also. And I'm just going to say, for starters, that the output is 1. We don't really know the state of the other one. But if that output is 1, we'd have a 1 here now. And if we have 0 and 1 as inputs, our output would be 0. And then that output would go to 0 here on this gate. And that's a case where that output is 1. Okay, so we're kind of at this steady state condition here. But now watch what happens if we change the S now to a 1, the input for setting it. Okay, now we have 1, 0 as the inputs, 1 and 0, which would be these. It would drive that output to a 0 here. And the output, then that would take this input to a 0. And now the output would be a 1. Now at first that seems, wait, I've got a 1 here and a 0 here. We have to take that output, connect it to this input. And now we have 1 and 1, which is now at a steady state of 0. So now Q equals 0 and Q naught equals 1. So we've basically changed the state of it. So I'll let you kind of go through the rest of the options here. For example, if we set R to 1 and leave S at 1, what happens? Or if we set S back to 0 and R to 1. Going through this exercise is kind of fun because you can actually see how the signals kind of propagate back and forth. But this is basically what's required to make a 1-bit memory device. So when you start talking about terabytes of data, not necessarily with solid state devices, but for example, if you had a device that had a terabyte of data, you'd need an unimaginable number of NOR gates to make that function. We can do the same thing, by the way, with NAND gates to create the same kind of circuit. So this is just kind of an introduction to kind of memory and how that works. We're going to be using that in some of the lab examples later on.